Okay, so, we always say we love it when our listeners point us towards some really cool research.
Yeah,
And this week, you definitely sent us down a fascinating rabbit hole.
definitely.
This paper from Advanced Sustainable Systems, Devi and their team, this is 2025. They're exploring this really innovative approach
Okay.
using seawater electrolysis.
Right.
Not just for clean energy,
Uh-huh.
but to actually capture carbon
Right.
and even create valuable materials all at the same time.
Yeah, that's right. This deep dive is all about how we can use electrochemistry to essentially coax seawater into precipitating minerals that can trap carbon. And what's really interesting here is how injecting CO2 during this process can actually supercharge the whole thing.
Exactly. And that's really what we want to unpack today.
Yeah.
Our mission for you listening is to dig into the core of this research and really show you how with just a bit of electricity and some added CO2, we can turn seawater into this amazing resource.
Yeah.
You get clean hydrogen, you get valuable materials, and you're locking away carbon all at the same time.
So win-win-win.
Exactly. It's like the ultimate win-win-win.
Yeah, for sure.
So think of this as your express route to understanding this cutting-edge science
Absolutely.
without getting bogged down in all the super technical details.
Right.
So to start off,
Yeah.
the basic idea is that when you run electricity through seawater to make hydrogen, something else kind of interesting happens as a byproduct.
Right. And that's what these researchers focused on. They looked at those byproducts.
Yeah.
Specifically calcium carbonate and magnesium hydroxide.
Okay.
And instead of just seeing them as a nuisance you have to deal with, they flipped the script and said, what if these minerals were the point?
Right. It's like a total shift in perspective.
Absolutely.
They were like, hold on, we can actually encourage the production of these minerals. And then that's where it gets really clever. They start experimenting with pumping CO2 right into the seawater during electrolysis.
Yeah.
And what they found was pretty amazing. This CO2 injection, it dramatically increases the formation of calcium carbonate.
Right.
Which, as we know, is a fantastic way to trap carbon dioxide.
It's a natural way to lock it away.
Exactly.
And while this opens up all these possibilities for both material production and carbon capture,
Right.
the researchers were also very upfront about the potential challenges. This mineral formation could increase the electrical resistance in the system,
Okay.
which could make it less efficient.
Right. Makes sense.
So that's definitely something they're looking at.
Right. So let's break down this dual potential of seawater electrolysis.
Yeah, let's do it.
Now, when most of us think about running electricity through water, hydrogen production, that's the first thing that pops into our minds.
Absolutely.
But can you give us a rundown of what's actually going on down at the electrode level in seawater?
Sure. So at the negative electrode, which is called the cathode, you have the production of hydrogen gas. And at the positive electrode, the anode, depending on the conditions, you might see oxygen gas being produced or even chlorine gas.
Oh, wow.
But as we already mentioned, there's this other important process happening right there at that cathode.
And that's the precipitation of the minerals, right?
Exactly.
We're talking about calcium carbonate and magnesium hydroxide.
You got it.
So what's actually causing them to form?
Well, the electrochemical reactions happening near the cathode, they actually cause the pH of the water to increase in that localized area.
Okay.
So think of it like this. You're adding something to the water that soaks up all the acidic bits, making it less acidic or more basic. And that's essentially what's happening with the pH near the electrode.
Got it.
And this higher pH, well, it makes it harder for the calcium carbonate and the magnesium hydroxide to stay dissolved in the water.
Okay.
And so they start to precipitate out as those solid minerals.
So this isn't a brand new phenomenon, is it?
Not at all.
The paper mentioned that this kind of mineral precipitation has actually been observed and even used before.
Yeah.
Like for things like protecting those big metal structures under the ocean.
That's right. They use it for cathodic protection.
Okay.
It basically creates a protective coating on underwater metal structures to prevent them from corroding.
Oh, cool.
And they've also been exploring it for coral reef restoration. Providing a solid base for new coral to attach to, and even as a way to fight coastal erosion by building up these mineral barriers.
Wow, that's amazing.
So yeah, the idea of precipitating minerals in seawater isn't exactly revolutionary.
Right. But what is revolutionary is the way we're thinking about these minerals now.
Absolutely.
We're not treating them as unwanted leftovers anymore.
Exactly. We're starting to see the potential of these minerals as valuable resources in their own right.
Exactly.
I mean, imagine using them in construction materials and manufacturing.
Yeah.
Even in environmental cleanup technologies.
That's really cool.
It's exciting stuff.
And then there's that really ingenious part that we talked about a little bit before.
Yeah.
Injecting the CO2 right there at the cathode during electrolysis. So how does that change the mineral precipitation process?
Okay, well, when you pump CO2 into the seawater, it dissolves and increases the overall concentration of what we call dissolved inorganic carbon.
Okay.
And this extra carbon combined with that higher pH around the cathode that's created by the electrolysis, it really accelerates the formation of calcium carbonate.
Okay.
That key mineral that traps carbon.
Gotcha.
So you're not just getting a mineral byproduct.
Right.
You're actively capturing that CO2 and locking it away in the mineral structure.
That's so cool.
It's a clever way to leverage a natural process.
Well, and of course, all this mineral buildup could potentially cause issues.
Right.
Like you were saying before about insulating the electrode.
Exactly.
And making the whole process less energy efficient.
Uh-huh.
So it sounds like it's a delicate balancing act.
Absolutely. Optimizing this process requires a deep dive into the chemical reactions at play.
Okay, so let's do that.
Let's get into the chemistry.
Let's delve into the chemistry behind this. I'm going to call it carbon capturing magic.
I like it.
So first, can you walk us through what happens at a molecular level when we introduce that CO2 into the seawater?
Sure. So when CO2 enters the seawater, it dissolves and reacts with the water molecules, forming carbonic acid. Now, this carbonic acid is not very stable, and it quickly breaks down further into bicarbonate ions and hydrogen ions. And, as you probably know, an increase in hydrogen ions means the water becomes more acidic, lowering the pH.
And the paper actually lays out those specific chemical equations that describe those reactions and that equilibrium between all those different forms of dissolved carbon.
Exactly. It's all there if you want to dig into the nitty-gritty details.
Cool. So then we apply the electric current.
Right.
So what happens when we introduce that voltage or current to this now CO2-enriched seawater?
Okay, so applying electrical energy, that's what drives those electrochemical reactions at the electrodes. And for our purposes, the crucial part is what's going on at the cathode. That's where we see the generation of hydroxide ions, or OH minus.
Hydroxide ions.
Yes. And think of these hydroxide ions as the opposite of those hydrogen ions we just talked about. They make the water less acidic or more alkaline. And this hydroxide production can happen through a couple of different pathways depending on the voltage that's applied.
Interesting.
It can happen through the oxygen reduction reaction, or ORR, or through the water reduction reaction, or WRRR.
ORR and WRR.
Exactly. And the paper provides those electrochemical equations for both reactions. Including the minimum energy required for each of them to occur.
So we've got this localized increase in hydroxide ions happening right next to the cathode. So how does that actually lead to the precipitation of the calcium carbonate and the magnesium hydroxide that we're after?
Okay, well, that surge of hydroxide ions has two major effects. First, it pushes the water beyond what's called the saturation point for magnesium hydroxide.
Saturation point.
Yeah, meaning the water simply can't hold as much of it dissolved anymore. And so it starts to precipitate out as a solid. The second thing those hydroxide ions do is react with the bicarbonate ions.
Which were formed.
Which were formed when we injected the CO2.
Right.
And this reaction, it shifts the balance of those dissolved carbon species, leading to a higher concentration of carbonate ions. And then those carbonate ions, they readily react with the calcium ions that are naturally abundant in seawater. And boom, you get calcium carbonate precipitation.
Wow. So it's like a chain reaction.
It is.
Set off by those hydroxide ions.
Exactly. And, the researchers emphasize that the saturation state of these minerals, which is basically how much of them can be dissolved before they start forming solids, that's critical. And it depends on the concentration of all the different ions floating around. And the total amount of dissolved inorganic carbon.
So it's a delicate balance.
For sure.
Now, you mentioned earlier that there are things happening over at the anode as well. So what kind of reactions are going on over there?
So at the anode, the primary reaction is what we call the oxygen evolution reaction. And that's where water molecules are essentially split to produce oxygen gas. But because seawater is salty, it's got all those chloride ions. At higher applied voltages, you can also get reactions where those chloride ions are oxidized, potentially forming chlorine gas.
Oh, wow. So we could actually be making chlorine gas as well.
Potentially, yes.
Interesting.
The paper goes into a bunch of possible reactions involving chloride.
Okay.
But it's important to note that chloride itself doesn't typically precipitate out as a mineral in this process.
Okay, so it stays dissolved.
For the most part, yeah.
Gotcha. Okay, so now we've got this interplay between the CO2 injection and the applied electricity.
So how do these two factors work together to give us the best results, like the most mineral production?
That's a great question, and the key really lies in the balance between the lower pH caused by the dissolved CO2 and the higher pH caused by those hydroxide ions generated at the cathode.
Okay.
It's a delicate dance between acidity and alkalinity.
I see.
The rate at which you inject that CO2 controls how much dissolved carbon is available for those reactions.
Okay.
While the rate of hydroxide production, which is directly linked to the electrical current, that dictates how effectively those carbonate and magnesium ions are driven out of solution to form those minerals. What's really fascinating is that the researchers calculated that for every 4 hydroxide ions generated, you can theoretically capture 1 CO2 molecule into calcium carbonate.
Wow.
And also produce 1 magnesium hydroxide molecule without significantly altering the overall pH from the injected CO2.
Okay.
So it's like this perfect stoichiometric balance.
Right. And then, to make things even more interesting, a high enough rate of hydroxide generation can actually further shift that carbonate equilibrium towards even more carbonate ions.
And that leads to
even more calcium carbonate precipitation.
Wow, so it's like a positive feedback loop.
In a way, yes.
That's amazing.
It's pretty cool.
So it sounds like a real balancing act.
It is.
So how did the researchers go about figuring out the ideal conditions to maximize mineral production?
Well, they conducted a very systematic set of experiments.
Okay.
Carefully controlling and varying a bunch of factors.
Wonderful.
Like the applied voltage, the electrical current flowing through the system, and the rate of CO2 injection.
Makes sense.
And they did all of this in specially designed electrochemical reactors. And by precisely measuring the amount of mineral produced under each set of conditions, they were able to pinpoint the parameters that gave them the best results.
So what did they learn about the impact of electrical energy, things like voltage and current, on the amount of mineral they could produce?
Well, in general, they found that the more electrical energy they pumped into the system, the more mineral they tended to get out.
Okay, that makes sense.
More energy, more product.
Right.
But they did notice a difference depending on which primary reaction was happening at the cathode.
Okay, so back to the ORR and the WRR.
Exactly.
Okay.
So when the oxygen reduction reaction was dominant, which happens at lower voltages, they got very little mineral.
Oh, wow.
And what they did get tended to stick really tightly to the electrode surface.
Okay.
But when the water reduction reaction took over at higher voltages, they saw a much more substantial mineral yield.
Interesting.
Although at very high voltages, the vigorous bubbling of hydrogen gas could actually cause some of that mineral to detach from the electrode.
Oh, that's interesting. I guess that could be good or bad depending on what you're trying to do.
Exactly right.
If you want to collect the minerals,
right,
maybe that's a good thing.
Uh-huh.
But if you want it to stay on the electrode,
maybe not so much.
Not so much.
Yeah, and they also found that the relationship between the amount of mineral produced and the applied voltage or current, it wasn't always a simple straight line.
Oh, really?
Yeah, it was what we call non-monotonic, meaning it went up and down.
Why is that?
It's likely due to the complex interactions between all those electrochemical reactions happening simultaneously at both electrodes.
Right.
Plus, you've got all those different ions floating around in the solution.
Okay, so it's like a complex dance of factors.
Exactly.
But I guess the key question here is, how did injecting CO2 change those optimal settings?
Yeah, so what they found was really important.
Right.
Injecting CO2 actually shifted the sweet spot for maximum mineral yield towards higher voltages and currents.
Okay.
Which makes sense if you think about it, because that added CO2, it makes the water slightly more acidic.
Right.
So you need to generate more of those alkaline hydroxide ions to counteract that acidity and really drive those precipitation reactions forward.
Right. So it's like the CO2 is pushing the system in one direction, and then you need to push it even harder in the other direction to get the results you want.
Exactly. And they actually saw this in their experiments.
Oh,
yeah. They found that the peak mineral production without any CO2 injection occurred at around METIsh 1.4 volts.
Okay.
But when they started injecting CO2, that peak shifted to a higher voltage of around METIsh at 2.0 volts.
Wow, that's a pretty significant shift.
It is.
Okay, so what about the CO2 itself? Was there like a magic number in terms of how much to pump in?
Yes, they actually discovered that for any given voltage or current,
Ah,
there was an optimal CO2 flow rate that maximized the amount of mineral produced
okay.
while keeping the energy consumption as low as possible.
Gotcha. So efficiency is key.
Always.
So what was that optimal flow rate?
Well, in their experiments, they found that a flow rate of 0.3 standard cubic centimeters per minute
Okay.
at nettage of 2.0 volts and 240 milliamperes.
Right.
That seemed to be particularly effective.
Okay, and why is that?
Well, their hypothesis is that this optimal flow rate helps maintain a relatively stable pH right near the cathode surface,
Okay.
which is where all the action is happening.
Right.
And that stability is crucial for efficient mineral formation.
Makes sense, because if there's too much CO2,
It could make the area too acidic and hinder the precipitation.
right, and too little CO2.
Well, then you might not have enough dissolved carbon to keep those reactions going.
So it's all about finding that Goldilocks zone.
Exactly.
Now, what about the total amount of CO2 they used?
Okay.
Did it matter if they injected a lot all at once or a little bit continuously?
So they tested that too.
Okay.
They experimented with different total volumes of CO2 injected either before they started the electrolysis or continuously during the process. And what they found was that the timing wasn't as critical as the flow rate,
Okay.
especially at those higher, more effective voltages.
Gotcha.
However, they did notice that at lower voltages, injecting a larger amount of CO2 up front seemed to reduce the amount of precipitation, whereas at higher voltages, more CO2 generally led to more mineral formation.
So again, it's about finding that balance,
It always is.
right, to minimize those big swings in pH around the electrode.
Exactly.
Okay, so we're putting all this energy in, we're injecting CO2,
Right.
and we're getting these minerals out that are locking away carbon. But fundamentally, what are these minerals that we're producing?
So through some high-tech analysis techniques like X-ray diffraction and thermogravimetric analysis,
Okay.
the researchers were able to determine that the primary mineral components were calcium carbonate.
Okay.
And that appears in two common forms called calcite and aragonite.
Calcite and aragonite.
Right. And the other main component was magnesium hydroxide,
Okay.
also known as brucite.
So could they control which of these minerals ended up forming?
To a certain extent, yes.
How?
Well, they discovered that both the applied voltage and the rate of CO2 injection had a noticeable impact on the types of minerals that preferentially formed. Generally speaking, higher voltages and higher CO2 injection rates,
Okay.
those favored the creation of more calcium carbonate relative to magnesium hydroxide,
Okay.
particularly when the water reduction reaction was the dominant process at the cathode.
Okay.
However, in that lower voltage regime, where oxygen reduction was more prevalent,
Right.
CO2 injection actually reduced the amount of calcium carbonate that precipitated.
So it seems like the CO2 injection has a different effect depending on the voltage.
Exactly. It's all about the interplay of those different reactions.
Right. And again, there was that sweet spot for the CO2 flow rate,
There always is.
right, that maximized the ratio of calcium carbonate to magnesium hydroxide.
It's all about finding that balance.
Right now, let's talk about the carbon sequestration aspect.
Yeah.
How much CO2 were they actually able to trap within these minerals?
Well, the study confirmed that CO2 is definitely chemically bound within that calcium carbonate structure,
Okay, good.
and the amount of CO2 captured increased as they applied higher voltages, with the largest amounts being observed under those water reduction reaction conditions.
Right.
Now, here's something interesting.
What's that?
They also noticed that at higher CO2 flow rates within that WRR regime,
Oh.
they saw a greater proportion of aragonite,
Mhm.
which is another crystalline form of calcium carbonate compared to calcite.
Mm-hmm.
So it seems like the CO2 flow rate not only affects the amount of carbon captured,
Right.
but also the type of calcium carbonate that's formed.
Wow, that's really cool.
Yeah.
And in terms of the final product, what were the ratios of those two main minerals?
Well, they were able to achieve a range of weight ratios between calcium carbonate and magnesium hydroxide,
Okay.
typically between around 60.4 and 40.60.
Okay, so pretty good mix.
Yeah, a pretty even split.
So what did these synthesized minerals actually look like?
Well, to the naked eye, they appeared as a white or slightly off-white powder
Okay.
with individual particle sizes ranging from very fine, around 0.02 millimeters.
Tiny.
Yeah, up to about 2 millimeters.
Okay, so a range of sizes.
Yes, and when they looked at them under a microscope,
Uh-huh.
they saw some distinct shapes depending on the electrochemical conditions.
Like that.
While calcite tended to form more cubic-like crystals, aragonite had a more elongated needle-like structure, and brucite appeared as numerous tiny interwoven fibers.
Oh, wow. So they look totally different.
They do.
Depending on how they're made.
It's really fascinating.
That is really cool. So now the study also explored the possibility of growing these individual mineral particles into larger, more substantial aggregates, like something you could actually use as a building material.
Exactly.
So how did they manage to do that?
Well, by carefully managing the electrolysis process over extended periods, they were able to grow centimeter-sized mineral aggregates directly onto the cathode.
Wow, so they could actually create these larger structures?
They could.
That's amazing. And what were the key factors in controlling that growth?
Well, there were three main things they had to control precisely. The overpotential, which is that extra bit of voltage beyond the theoretical minimum needed for the reactions to occur.
Okay.
The flow rate of the CO2 and the continuous circulation of the seawater.
Oh, why into circulation?
That ensures a steady supply of the necessary ions to the cathode surface.
Okay.
So it's like providing a constant stream of building blocks for those minerals to grow.
Right. And they observed something interesting about the current density.
Yeah, they found that as the process went on, the current density tended to decrease.
Okay. And why is that important?
Well, surprisingly, it seemed to help the minerals adhere to the electrode and grow without detaching.
Oh, so it actually helps with the attachment.
It did.
Interesting.
Yeah, it's like the lower current density created a more stable environment for those minerals to grow.
So they could control the size of the aggregates.
Yes.
What about the shape?
They found that they could actually influence the overall shape of those mineral aggregates.
Okay.
By using cathodes with different shapes. Oh, interesting. So the shape of the electrode actually dictated the shape of the mineral deposit.
Exactly.
That's so cool.
Yeah, it is. And it opens up all sorts of possibilities for designing these materials.
Right. Like you could potentially create aggregates with specific shapes.
You could.
For different applications.
Exactly.
Very cool. Now, these aggregates, they weren't just solid, dense blocks, were they?
No, they weren't.
The paper mentioned that they had a certain degree of porosity.
Right.
So can you explain why that's an important characteristic?
Absolutely. So the aggregates naturally exhibited some level of porosity, and this porosity was actually linked to which reaction was dominant at the cathode.
Okay, so back to the ORR and WRR.
Exactly.
Right.
So the oxygen reduction reaction tended to produce denser, less porous, and stronger aggregates. While the water reduction reaction resulted in more porous structures.
Interesting. And why is that?
Well, it's likely due to those hydrogen gas bubbles forming during the WRR and creating void spaces as the mineral grew. Oh, I see. So those bubbles are like little architects.
Yeah, you could think of it that way.
Carving out spaces within the material.
Exactly.
Now, why is that porosity beneficial?
Well, it's actually quite important because it allows fresh seawater containing those calcium and magnesium ions and dissolved CO2 to continue to reach the reaction sites on the cathode surface.
Okay.
Even as the mineral layer thickens.
So it's like the pores are creating channels for those reactants to flow through.
Exactly. They keep those pathways open.
Very clever.
It's a pretty neat self-regulating system.
And what size were those pores?
They observed pore sizes within the aggregates ranging up to 10 millimeters.
Wow, so some of them were quite large.
Yeah, some of them were.
Interesting. And the composition within these larger structures, was it uniform throughout?
Interestingly, no, they found that the composition wasn't entirely uniform.
Really?
Yeah, there was a tendency for a higher concentration of magnesium hydroxide to be present closer to the cathode surface.
So like a gradient of composition within the aggregate. Exactly.
Yeah, and they also identified a wider variety of those mineral forms or polymorphs in these longer duration experiments.
They did.
Which ones?
They found calcite, aragonite, vaterite, and of course brucite.
Okay, so even more variety in those longer experiments.
Yes, and what's cool is that the researchers emphasized that by carefully adjusting the electrochemical parameters and the CO2 injection rate, they could exert a degree of control over which of those mineral forms predominated.
Wow. So they could really fine-tune the composition and structure of these aggregates?
They could.
That's really impressive.
It's pretty remarkable what they were able to achieve.
Now, what about the stability of these aggregates?
Okay, good question.
Like, could you just leave them out in the elements?
Well, they tested that.
And
They found that the aggregates were quite stable in deionized water
okay.
and in artificial seawater.
So they can handle being submerged.
Yes, but they did observe that the aggregates would break down into a fine powder if exposed to highly alkaline conditions. Interesting. So they have a limit.
They do.
And why do they break down in those alkaline conditions?
They believe it's because the high pH weakens the forces holding the calcium carbonate and magnesium hydroxide components together.
Okay, so it's like the glue that holds them together dissolves away.
Yeah, that's a good analogy.
Now, here's something that I found really interesting.
What's that?
The potential for these aggregates to store even more CO2
Right?
through a process called carbonation of the magnesium hydroxide.
Yes, that's a really cool aspect of this research.
So can you break that down for us?
Sure. So that magnesium hydroxide within the aggregate structure, it can actually undergo a further chemical reaction with CO2
Okay.
to form various hydrated magnesium carbonates, like hydromagnesite and nescianite.
Okay.
And this essentially provides an additional pathway for long-term carbon storage within the material.
So it's like double dipping on the carbon capture.
Exactly. You're using the same material to capture even more CO2.
That's amazing.
And the researchers calculated that an aggregate made up of a 50-50 mix of magnesium hydroxide and calcium carbonate could theoretically store a significant amount of additional CO2 through this process.
Wow. And did they actually see this happen in their experiments?
They did. They observed around 80% conversion of the magnesium hydroxide to hydromagnesite.
Wow. So it's not just theoretical.
Nope, it actually works.
That's fantastic. And this carbonation process.
Yeah,
It has other advantages beyond just storing more CO2, doesn't it?
it does.
What else does it do?
Well, they found that this carbonation process also altered the internal structure of the aggregates, generally making them less porous and significantly increasing their overall strength.
Okay, so it makes them more durable.
Exactly. For
Yeah.
example, the compressive strength, which is a measure of how much squeezing force a material can withstand,
Right.
that jumped from around 1.4 megapascals to over 6 megapascals after carbonation.
Wow. So more than 4 times stronger.
Yeah, it's a significant improvement.
That's incredible. So what are the potential real-world applications for these mineral aggregates?
Well, the paper hinted at some pretty exciting possibilities.
Look at.
Well, for starters, the particle size distribution of the aggregates they synthesized, it was actually quite broad, and in some cases it even met the specifications outlined in ASTM C33.
And what is that?
That's a standard for aggregates used in concrete production.
Oh, wow.
So this immediately suggests a direct application in the construction industry
Okay.
as a sustainable alternative to conventional aggregates.
So we could be using these aggregates to build buildings and roads and bridges.
Potentially, yes.
That's amazing. What else?
Well, beyond construction, they could potentially be used as raw materials in the manufacturing of cement blasters paints,
Okay.
even in various environmental remediation applications,
Okay.
things like beach replenishment, creating artificial reefs,
Wow.
or other habitat restoration projects.
So the possibilities are really wide open.
They really are.
This whole approach sounds incredibly promising.
It is.
So looking ahead, what are the key takeaways and future directions for this research?
Well, the study really highlights the incredible potential of controlling those electrochemical parameters and the injection of CO2
Right.
to tailor the properties of these calcium carbonate and magnesium hydroxide minerals
Okay.
and those larger aggregates that they form.
Right.
And the researchers believe that there's tremendous potential for optimizing the energy efficiency of this whole process,
Right.
not just for capturing carbon, but also for producing valuable green hydrogen as a byproduct.
So we could be getting clean energy and sustainable materials all in.